Welcome to the module 3 of the 10th chapter. This is on the constructions with straightedge and compass. I think all of you are familiar with the constructions like bisecting a given angle and construction of the perpendicular bisector of a given line segment. And I am sure that none of you ever tried to trisect a given angle. Why? In this module and next module, I will prove that there are angles which cannot be trisected with straightedge and compass. And the most interesting fact is that though this problem is geometric in nature, I will give proofs which involve algebra. In the 500 BC, the Greek geometers devoted their sincere effort to three famous constructions. One is to trisect an arbitrary angle. Second is to construct a cube whose volume is double of that of a given cube. And the third is to construct a square whose area is equal to that of a given circle, using only an unmarked straightedge and collapsible compass. The compass, which was used by the Greek geometers and that we use today, are completely different. The compass we use today are movable. That is, we can set an arbitrary radius using these compass. But at that period, the Greek geometers could not. They were rigid compass, which we refer as collapsible compass, and by an unmarked straightedge, we mean a ruler which can be used to draw a straight line but cannot be used for measuring any length. That is the rulers or straightedge where there is no marking for measuring some length. We have a series of results which shows that all the constructions which can be done using an unmarked straightedge and a movable compass can also be done using an unmarked straightedge and collapsible compass. So, it does not make any difference whether we are using a collapsible compass or a movable compass. But the most important to note that we are using the straightedge which is unmarked. That is, we can use this only to draw a straight line, not to measure any length. In the subsequent two modules, we prove that such constructions are impossible. What especially interesting is that although the constructions were to be geometric, proofs of their impossibility involves algebra. In this module, we show how these problems are related with algebra. In the next module, we apply algebraic results to prove impossibility of the constructions originally attempted by the Greeks. What we can do with an unmarked straightedge and a collapsible compass are drawing straight lines and circles. Let me first recall some elementary constructions using straightedge and compass. Obviously, we will use these constructions in our subsequent proofs. First, let me recall construction of perpendicular bisector of a line segment. Let AB be a given line segment. Draw a circle of center A and radius approximately more than half of AB. Then draw another circle of center B and same radius. Suppose the latter circle intersect the previous circle at M and N. Then MN is the perpendicular bisector of the line segment AB. Following this construction, we can construct two mutually perpendicular straight lines. Now, we demonstrate the method for constructing bisector of an angle. Consider an arbitrary angle XOY. Then draw the circle with center O of arbitrary radius r that intersects OX at A and OY at B. Draw the circle with center at A and same radius r. Then draw the circle with center at B and same radius r. Suppose that these two circles intersect at P and O. Then the line OP is the bisector of the angle XOY. Finally, I will demonstrate a method for constructing lines which is parallel to the given one and passes through a point M not on AB. First, draw the circle with center A and radius AM. Denote this radius AM by R. Then draw the circle with center C and radius R. Then draw the circle with center M and the same radius R, which intersects the previous circle at A and N. Then the line MN is the desired line, that is, this MN is a line, actually this is unique, so MN is the line which is parallel to the given line AB and passes through the given point M. How does algebra involve with these constructions? Note that in all of these constructions, the points which are intersections of either two lines or a line and a circle or of two circles take an important role, and hence the line segments between two such points takes an important role. Actually, not only the line segments but also the length of the line segments. in the subsequent discussions, we show that there are positive real numbers A such that a line segment of length A can be constructed, and there are positive real numbers B such that it is impossible to construct a line segment of length B such that the end points are either intersection of two lines, or intersection of a line and a circle, or intersection of two circles, and thus algebra comes into the picture. If we want to measure length of a line segment, so there should be a standard line segment which we call unit, that is 1 unit in length. Let us construct two mutually perpendicular intersecting straight lines. This construction is possible by straightedge and compass only, that already I have discussed, and call the point of their intersection as 0, 0. Then we can measure the unit length by compass and locate the points 1, 0, minus 1, 0, 2, 0, minus 2, 0 and 0, 1, 0, minus 1, 0, 2, 0, minus 2 and so on, step by step on these mutually perpendicular lines. Thus we get two axes which we call x and y axis. One must note here that these are not actually x and y axes of the Euclidean plane, since each point on the axis in the Euclidean plane has a numerical label, whereas here our investigation is towards the points which can be labeled by using straightedge and compass only from the given 1 unit length. In other form, each point in Euclidean plane has a coordinate, and our problem is to distinguish the points which can be located by straightedge and compass only from the unit length. For this, first we distinguish the real numbers alpha such that a line segment of length mod alpha can be constructed, and we introduce a new term, constructible numbers. A real number alpha is constructible if we can construct a line segment of length mod alpha in a finite number of steps from this unit length by using a straightedge and compass only. Discussion before this definition shows that every positive integer as well as every negative integer is constructible. Now we give some examples of real numbers which are not integers, still are constructible. First, we show that root 2, though it is not a rational number even, still it is constructible. First, construct two mutually perpendicular straight lines OX and OY and assume that they intersect at O. Then mark OA from the x axis of unit length. Erect perpendicular at A and mark AB with unit length. Then OB is a line segment of length root 2. Thus, we see that since we can construct two mutually perpendicular straight lines, we can erect perpendicular at a given point on a straight line using only straightedge and compass. So, it follows that using only a straightedge and compass, we can mark a line segment of length root 2. Hence, according to our definition, root 2 is a constructible real number. Now, we show that not only root 2, but an integral multiple of root 2, say for example 3 root 2 is constructible. Actually, the method which I am going to follow here can be used to show that product of any two constructible numbers is also constructible. For example, here I take two numbers, one as 3 and other as root 2. Draw two intersecting straight lines OX and OY as shown in the figure. Start at O and lay off OA of length root 2 on OX. Lay off OB of length 3 and OP of length 1 on OY. Connect PA and then construct a line through B that is parallel to PA and which intersects OX at Q. Recall that we can construct a line which is parallel to a given line, here say PA, and passes through a given point here B using only a straightedge and compass. Thus, the total constructions here is possible using a straightedge and compass only. Can you mark out the line segment which is of length 3 into root 2? I can give you a clue. You can use the similar angled triangles, that is the properties of similar angled triangles. Can you find out two triangles here which are similar triangles? Note that triangles OBQ and OPA are similar angled triangles, and hence we have OQ by OB is equal to OA by OP, which gives us the length of OQ by 3 is equal to root 2 by 1, and thus the length of OQ is 3 into root 2. Thus, we see that using only straightedge and compass, it is possible to construct a line segment, say OQ, whose length is 3 root 2. Thus, we see that root 2 is constructible. Now, my question is that is it possible to construct a line segment of length cube root of 2? Also, we see that 3 root 2 is constructible, and I also remarked that product of any two constructible real numbers is constructible. If A and B are constructible where B is non-zero, then is it possible to construct a line segment of length A by B? Now we will try to give an algebraic structure to the collection of all constructible real numbers, and which will help us to identify all the constructible real numbers. Now we show that the set of all constructible real numbers is a subfield of the field of all real numbers. Let K be the set of all constructible real numbers. Then 1 and 0 are in K, which ensures that K is a non-empty subset of R. Consider two elements A and B from K and assume that both A and B are positive. Draw a straight line OX by the straight edge. Now start at O and lay off OA of length A. Then start at A and lay off AB of length B as shown in the figure. Thus, we see that the real number A minus B is constructible. That is, A minus B belongs to K. Now we show that A by B is also constructible. For this, draw two intersecting straight lines OX and OY as shown in the figure. Start at O and lay off OA of length A on OX. Lay off OB of length B and OP of length 1 on OY. Connect AB and construct a line through P that is parallel to AB. As I have shown you earlier, that using only straightedge and compass, it is possible to construct a line PQ which is parallel to a given line AB and passes through a given point P which is not on the line AB. Assume that this line PQ intersects OX at Q. Now I will use the properties of similar angled triangles to find out a line segment in this picture which is of length A by B. As shown in this figure, you note that I have assumed here B actually to be greater than 1. So, A by B will be a line segment which is of length smaller than A. So, it might be that OQ is the line segment of length A by B, and I will show that actually this is. The triangles OBA and OPQ are similar angled triangles from which we have length of OQ by the length of OP is equal to length of OA by length of OB, which gives us length of OQ by 1 is equal to A by B. That is, OQ is a line segment of length A by B. Thus, A by B is a constructible real number and hence A by B belongs to K. Hence, given any two members A, B of K, we see that A minus B and A by B are also in K, provided B is non-zero, and hence K becomes a subfield of the field of all real numbers. If A and B are not positive, an obvious manipulation according to their signs shows that both A minus B and A by B are still constructible. So, immediately it follows that if A and B are constructible real numbers, then their sum A plus B, their difference A minus B, their product AB, and A by B if B is non-zero are constructible real numbers. You know that since R is a field with characteristic 0, every subfield of R is also of characteristic 0, and hence the field of all constructible real numbers K is also of characteristic 0. So, Q will be a subfield of K, and which implies that every rational number is constructible. Recall that I have already proved root 2 is constructible. Now I show that if A is a constructible positive real number, then root over A is also a constructible real number. Let OA be a line segment of length A. Extend AO up to P so that OP is of unit length, and draw a semicircle with PA as diameter. Let the perpendicular to PA at O intersect the semicircle at Q. Then the triangles OPQ and OQA are right angled triangles. From the fact that the semicircular angle PQA is a right angle, it can be proved that the angle PQO is equal to angle QAO, and angle QPO is equal to angle AQO. Thus, triangle OPQ and triangle OQA are similar angled triangles, and so we have the length of OQ by the length of OA is equal to length of OP by length of OQ, which implies that the length of OQ square is equal to A, and hence OQ becomes a line segment of length root over A. This shows that root over A is a constructible real number. Thus, we see that all rational numbers as well as many irrational numbers are constructible. Though we have proved that all constructible real numbers forms a subfield of R, still we do not have any necessary and sufficient condition such that a given real number A is constructible. In the next module, we will prove a necessary condition for constructibility of a real number and use the condition to prove impossibility of the three famous constructions.